All right, so let's get started. So starting from last few lectures, we started zooming into an airplane. So we started by looking at the incompressible potential flow in the far field of an airplane, right? Especially far away behind an airplane and also far beneath an airplane. Like we see the momentum balance around the airplane that's providing both lift and induced drag. So over the next few lectures, we are going to be slowly zooming in to the airplane. And today we are going to be looking again at the induced flow of an airplane, but now much closer to the airplane, and look at what is the effect of the plane form, for example, right? How would the distribution of lift change as you change the angle of attack? And again, we're going to be using the very nice property of incompressible potential flow, that if you add up two potential flow fields, the new flow field is going to be a valid flow field. All right. And starting from next week, there is no class on Friday, it's a holiday, but starting from next week, we are going to be further zooming in. So instead of looking at over the length scale of the span, we are going to be further zooming in and going to the length scale of the chord, right? Looking at the potential flow around the airfoils. And finally, in our viscous flow section, we are going to be zooming onto the airfoil, into the boundary layers, and see how the flow behaves in the thin layer around the airfoil. So today is the first lecture of zooming in. Now, instead of looking at the far field, we now start to look at around the airplane. Now, around the airplane, it is no longer sufficient to think about the flow around the airplane as two trailing vortices going from the wingtips to infinity, right? We now start to having to consider that there is a distribution of trailing vortices coming from almost everywhere on the wing. So whenever there is a change, there is a gradient of lift per span, there is going to be a vortex coming out, right? The only time when you have no vortex coming out is when you have a uniform lift per span. So the circulation around the wing would be constant as you move along the span, and there is no vortex that has to come out. As long as you have a change of circulation, right? Because the circulation as you move, so as you move along the span, any change of the circulation actually has to come out of the control volume. So if you draw a control volume, that on one side, let me actually draw it a little bit better. On one side, it's over here, and on the other side, it's over a different location around the span, and you actually connect these two faces, right, to form a closed control volume. Any circulation on the green control volume has to be an integral of vorticity that goes in, right? Any circulation on the black volume has to be vorticity coming out. If there is a difference in the circulation and the fact that vorticity cannot have any divergence, which means the total integral of the flux of vorticity in the control volume has to be zero. So if there is a change of the circulation between the green and the black one, then there must be vorticity coming out of the red surface that connects these two contours, right? And we have looked at the evolution of vorticity equation, that any place in the flow field you would find non-zero vorticity would be downstream of the solid surface, right? Remember our evolution equation that says the material derivative of omega over rho has to be equal to omega a dot with the divergence, not the divergence, with the gradient of the velocity field, right? So that's it basically says that if omega is zero upstream, then there cannot be any material derivative of omega, which means the omega would not increase from the existing zero value. So only place where vorticity would be non-zero would be on the wake. Okay, so that means if there is a change of circulation along the span, there is going to be non-zero vorticity coming out. Okay, so today let's look at how, first of all, how the induced flow by the collection of vorticities that comes behind the trailing edge and the vorticities that are bound in the wing, right? How would that depend on angle of attack as we change the angle of attack? One of the nice thing about incompressible potential flow is the flow field. Let's say the induced flow being UI, that's induced flow. One of the nice thing is that this can be expressed as a U induced zero at zero angle of attack, okay, plus the angle of attack alpha times a UI prime. So in other words, the induced flow is an affine function, right? Sometimes it's just called a linear function of the angle of attack. So for example, if all the airfoils are symmetric and they have zero incidence angle to the airplane, then the induced flow at zero angle of attack would be zero because nowhere has any lift, right? And then the induced flow is just proportional to the angle of attack. If there is any incidence angles or non-symmetric airfoils, there is going to be some fixed induced flow at zero angle of attack, and then the additional induced flow at non-zero angle of attack would just be linear with respect to any angle of attack. So let's start by looking at why this is the case. In this flow field, the condition that has to be satisfied, right? So first of all, in the free stream, away from the airplane, away from the lifting surfaces, the flow has to be a valid flow field, and that is automatically satisfied if you construct the flow field as the summation of the induced flow fields by a collection of vortices. Right? The induced flow of any vortex is a valid flow field. If you add them together, it is going to be a valid flow field. So that is by construction correct. But there is an additional constraint the flow field has to satisfy. That is the relationship between induced flow on the wing. So if you have, for example, a induced downwash, let me just call W induced on the wing, okay? That induced downwash combined with the free stream, U infinity, forms an angle of attack, right? The free stream, let's think about the free stream has an angle of alpha with respect to the axis of the airplane. So that's basically the angle of attack of the airplane, right? So that U infinity combined with the induced flow is going to modify the angle of attack on this particular cross-section of the wing. And that modified angle of attack leads to a lift, right? Leads to basically the angle of attack plus the airfoil cross-section is going to determine what is going to be the sectional lift coefficient on the cross-section. And that is going to give us what? Through the Kutta-Joukowski theorem, the lift per span, right? Lift per span is equal to what function of the local circulation on the cross-section, right? So that's something you should have studied in unified fluids, right? So that's basically let me just spell it out. Kutta-Joukowski theorem. So lift per span is the circulation times rho times U infinity. All right. So basically that relates how much circulation you have inside the wing, right, around the wing, with how much lift you have. And now lift per span is a function of the lift coefficient, which is a function of the local angle of attack, which itself is a function of the induced flow here, which is a function of the circulation, right, which leads to the trailing vortices. So that completes a loop, right, a loop of dependencies that you have to solve for you to figure out what is the induced flow, right? So let me basically write it down here. So lift per span leads to a circulation. So let me say just the L over B, or delta L over delta B, because that changes over the span, is going to determine what is the distribution of circulation, right? Circulation bound. So that's bound on the wing. And from the change of the bound circulation on the wing, that's going to lead to a circulation of the trailing vortices, right? That's just a deterministic function. And from the trailing vortices, it's going to give you the induced flow on the wing, all right? And the induced flow on the wing is going to tell me what is the angle of attack, right? Actually, the induced angle of attack. So the real angle of attack seen by the cross-section is actually alpha, let me just call alpha infinity minus alpha induced, all right? And alpha infinity minus alpha induced is going to lead to the CL, the lift coefficient on that cross-section. And the lift coefficient on that cross-section multiplied with half of rho v infinity and then multiplied by the local chord length is going to give us the lift per span, right? Is this circle, is any part of the circle confusing for you? Or do you understand why there is a deterministic relation kind of connecting one to the other? All right. So as you can see, some of these relationships are local, right? For example, the lift per span leads to let me just use green to denote local relations and red to denote global relations. So from the bound vortex to the trailing vortices, it's a non-local dependency, right? Because you have to take derivative of the bound vortices to get the trailing vortices. And from the trailing vortices to the induced flow is also global. It requires an integral, not even just a derivative, right? You have to integrate the induced flow coming from all the trailing vortices to get the induced flow. And the rest of them, from the induced flow to the induced angle of attack and to the angle of attack seen by the cross-section to the lift coefficient, these are all local effects. Yes?
What do you mean by induced angle of attack?
What do I mean by induced angle? That's a good question. So let me explain it a little bit further. So the induced angle is the angle between the free stream and the flow field seen by the cross-section. So let me, the green arrow is the free stream. And if you add the free stream with the induced flow, the purple arrow, right, is the flow field seen by the cross-section. And the angle between the free stream and the flow field seen by the cross-section, that angle is alpha induced. All right, that is why the actual angle of attack seen by the cross-section, this angle, let me use yet another color, this angle is alpha minus alpha induced. Let me say alpha infinity. And the green one is alpha infinity, right? All right. Make sense? All right, and it's the alpha infinity minus alpha I that determines the local lift coefficient. All right, okay, and then let's start to look at this dependency here, and especially the linearity of it. Okay, so from the lift coefficient from the lift per span to the strength, the circulation of the bound vortex, as we see from the Kutta-Joukowski theorem, it's a linear relationship, right? If the lift per span doubles, the circulation doubles. And from the bound vortices to the trailing vortices is also a linear relationship, right? It is basically taking the difference between the circulation on different cross sections to get the strength of the trailing vortices, right? A simple difference is a linear relationship. And from the trailing vortices to the induced flow, right? That's Biot-Savart law. That's also linear, right? It's if you remember the integral, if the circulation doubles, the induced flow would just double. And from the induced flow to the induced angle, right? So we are just dividing the vertical component of the induced flow by the free stream velocity to get the induced angle. And so this is linear. This is linear if ui, the induced flow, is much less than u infinity, right? So if the induced flow is a very small, then the alpha angle would just be computed by dividing wi by u infinity, right? Okay, and then of course from alpha I to alpha infinity minus alpha I is a affine relationship. It's linear. It's basically affine means a constant term plus a linear term, right? And then from the angle of attack seen by the airfoil to the lift coefficient, right? As we learned in unified, if we assume everything is if by like if we assume the airfoils are inviscid and the thin by the thin airfoil theory, the lift coefficient is CL would be equal to CL0 at 0 angle of attack plus 2 pi, right, times alpha infinity minus alpha I, right? Again, it's an affine relationship. All right. And of course, from CL to the lift coefficient per span, it's just a multiplication of 2 rho v infinity squared times the local chord length, right? So that kind of completes all this relationship. Every relationship is linear or affine, which means that we get a global. It's not local, right? The linear relationship may be a linear relationship between the induced velocity at one point and the trailing vortices at a different point. But the whole thing is linear, which means if we put all of them into equations, they are all linear equations, right? It's a collection of linear equations, a system of linear equations that governs basically you can for example use either the strength of the bound vortices as unknowns and solve them, right? The result is going to be actually a linear function or affine function of this alpha infinity, right? This logic basically tells us that the induced flow can be expressed as a 0 angle of attack induced flow plus a linear term that linearly depends on, I should say, the angle of attack seen by the entire airplane. All right. Any questions on this whole linear relationship and the solution being actually linear with respect to this alpha infinity? Okay. So just as an example, how the lift distribution depends on the angle of attack, let's actually review the optimal elliptical distribution, right, on the elliptical wing. So let's assume we have symmetric airfoils and untwisted wing and elliptical planform. Okay, so that we know that's going to give us at any angle of attack, it's going to give us an elliptical distribution, which is going to create a uniform downwash on the entire wing. And in that case, did you? I think at least when I look at old unified notes, there is the derivation where the induced flow is actually equal to the lift coefficient divided by pi times the aspect ratio, which is B over C, right? Have you seen this equation? Yes? No? I see some people shake their head, some people nod their head, so I'm a little bit confused. Okay, so have you analyzed the elliptical distribution being like optimal in the sense of least induced drag? Have you looked at the elliptical lift distribution at all? No? Not really? Okay. Sure. So maybe the most important thing I should say here is let me put some like sections on Anderson's for you to actually read about the elliptical distribution. I mean, the derivation itself is not as important. The most important thing is the kind of intuitive understanding, right? So maybe let me just draw a box over here that kind of introduces the elliptical distribution. Okay, so if you have a uniform lift distribution, okay, so the lift, if the lift is uniform across the whole span, so that's the span. Okay, what are the system of trailing vortices coming out of the wing? Just the application of what we discussed on the previous slide. Where does vortices come out? Only at the wingtips, exactly. We are only differentiating the lift per span at different cross sections, right, to get the trailing vortices. So the gamma would be concentrated at the wingtips. As a result, that's something from your homework if you started it. What does the downwash distribution look like along this wing? Is the downwash maximum in the center or maximum at the two ends? At the two ends, right? At the center, it has minimum downwash. At the two ends, it has maximum downwash. So the downwash distribution, so let me say the green is lift, and the downwash distribution looks pretty much like that. Okay, and as a result of that, the lift at the two ends are going to be tilted back a lot. Okay, and if you integrate the tilted back lift, you're going to see you're going to see a very inefficient lift distribution in the sense that to create the same lift, it tilts backward the lift by actually a lot. Similarly, if you look at the induced flow in the far field, you're going to see very high velocity, right, around the concentrated vortices, and lower velocity in the middle. So the concentrated velocities around these vortices again introduces a lot of kinetic energy, a lot of low pressure regions. That's going to give you a lot of induced drag. So both from a near field and far field perspective, you're going to see the uniform distribution is very inefficient. A efficient distribution of lift can be analytically worked out to be something that has a lower lift per span at the two ends and the maximum lift per span in the middle. And the analytical solution turns out to be an elliptical distribution, right? So basically the lift per span is proportional to square root of 1 over y divided by b over 2 squared. Okay, so what that means is that if you draw a line that encompasses the tip of the lift distribution, that line is 1/2 of an ellipse. All right, and so if you look at the trailing vortices coming out of that distribution, what does it look like? Is the vorticity still coming out as two concentrated vortices at the wingtip? No, right? Still, the concentration is going to be the maximum at the wingtips because the derivative of this lift per span function is maximum. It's actually infinity at the two ends. But the strength is going to be complemented by weaker vortices in the middle. Okay, so these weaker vortices in the middle would actually create an upwash as opposed to downwash at the wingtip. That balances with the downwash created by the two concentrated vortices at the wingtips, and as a result of that, the downwash from this elliptical lift distribution would actually be uniform. Right? This is the W, the Z component of the induced flow would be uniform. Okay, and it turns out that this Wi, so Wi, the induced flow, is actually equal to minus of U infinity CL, the overall lift coefficient, right? Which means the lift divided by half of rho v infinity square, and then divided by the total area of the wing of elliptical shape. Okay, then further divided by pi b over c. Right. So that's the uniform induced flow within the two wingtips. Right. Beyond the wingtips, there is still kind of a upwash that decays as you go to infinity, right? So that's similar. I mean, qualitatively similar to what happens over here, right? For the uniform distribution. So this is uniform elliptic distribution. Okay, any questions on this? So that's I think what is the extent of at least what is previously taught in Unified about. No, it's no longer. Okay. So on 3D finite wings, what is the end of the lectures? Like where did you go to? Okay. Anybody remember what is the extent of the coverage on 3D wings?
We did the kinetic energy induced drag, Trappist plane.
Okay. Trappist plane induced drag, but like no. Okay, so that's fine. So the derivation is a little bit mathematical. I mean, it's not really that important to actually follow completely the derivation. The only thing you need to know is that this kind of for a fixed span, this kind of distribution is optimal. And there is a little bit of a discussion in the sense that if you look at the, I think the English speak file is like actually strictly follows the elliptical distribution, right? That's at the time when this derivation first came out. But later on, people found out that if you don't follow from a strictly aerodynamic point of view, right, instead of fixing a span, it is more efficient to fix the weight of the wing and optimize the induced drag. And fixing the weight of the wing means fixing the structural weight, right? So if you can further reduce the lift at the tips of the wing and increase the lift in the middle a little bit, so make it taper a little bit faster, that's a better strategy in the sense that it reduces the moment, right? The moment at the root of the wing by reducing the lift at the tips. So that'll allow you to increase the span even further with the same weight of the wing. So if you look at most of the lift distribution we use nowadays, it goes down a little bit further than the elliptical distribution, but still it follows the same trend: more lift in the middle, less lift towards the two ends. All right. Okay, so this is a special case that you have uniform distribution of lift, and if you do have a elliptical, not only have an elliptical lift distribution, but actually have an elliptical plane form. Let's actually look at what happens. A plane form means that not only the lift distribution, but the chord length is proportional to square root of 1 minus 2y over b squared, right? So that's like that's a wing that looks basically like an ellipse. So that's an airplane. That's what the airplane would look like roughly. Okay, so if you have chord distribution like that, you can actually work out what happens. So not only the lift distribution is going to be elliptical at any angle of attack, right? So that's basically what's special about the elliptical planform. So this is because everything in the loop is consistent. So now let's actually try to go through this exercise, go through the loop for this elliptical planform with symmetric airfoil and zero twist, okay, to see what's happening throughout this loop. So first of all, let's see that if we have a lift per span that is proportional to this elliptical function. Okay, what that means is the trailing vortices is going to come out in a particular way that leads to the induced flow being uniform. Right? If the induced flow is uniform, then the induced angle of attack is uniform. And actually, we know how it works out. It works out to be it works out to be basically the induced flow divided by u infinity, which is gives us the classical formula of the induced angle of an elliptical distribution. So CL divided by pi times aspect ratio. Okay, so now if the induced flow is uniform, that means that the angle of attack seen by every cross section is actually the same. So basically alpha infinity minus alpha I would be actually CL divided by pi b is actually equal to alpha infinity minus CL pi b over c, right? And that leads to the lift coefficient. So lift coefficient is, let's assume the thin airfoil theory result to be true. So reality might be a little bit different from 2 pi, but not that much different. So CL is going to be 2 pi times that angle, which means it's 2 pi times alpha infinity minus CL. And by the way, if every cross section sees the same angle of attack, right, then the overall CL of the wing is actually the same as the each individual uniform CL, right, of the different cross sections. So that actually gives us an equation to solve, right? And not only that, the CL can be computed as a function of the local angle of attack, it actually is a function of the global angle of attack, right? And that CL goes back to the elliptical lifted distribution, because the CL is actually the same across different cross sections. And to get the lift per span, you just need to multiply CL by the dynamic pressure, half rho v infinity squared, which is the constant, right, for different cross sections, and further multiplied by the chord length, which is elliptical, right? So this is basically because of elliptical chord distribution. All right. So that completes the loop and shows us that if you have an elliptical planform for like a untwisted wing, you actually always get a elliptical lift distribution no matter what angle of attack you are at. All right. Any questions on this? this can also helps us work out what is the lift coefficient, right? So if you solve this equation by actually collecting the terms, you get CL 1 plus, so basically move the other CL term onto the left hand side. You're going to get plus 2 divided by pi times aspect ratio is equal to 2 pi alpha infinity, right? Or CL is equal to 2 pi divided by 1 plus 2 over pi aspect ratio times alpha infinity, right? Okay, so that's nice because it also tells us for different aspect ratio how the lift coefficient depends on the overall angle of attack. So if this is alpha infinity, this is lift coefficient. If you have infinite aspect ratio, the denominator is just 1, right? You would have a straight line that goes up to 2 pi alpha infinity. All right. On the other hand, if you have a, of course, non-infinite aspect ratio, you're going to have a slightly larger denominator, and the line would be slightly lower. So, for example, if you have an aspect ratio of, let's say, 8, all right, then the 2 over 8 pi is about 1 over 4 pi, right? It's like, so if B over C is 8, you get 1 over 4 pi, which is like 12, and you get about 1/12 difference between the actual slope you get versus a infinite span glider, right? So that kind of gives you a rough sense of, so basically there is a 1/12 difference for B over C equal to 8. All right. So that kind of gives you a sense of how big the discrepancy is. It's not that significant for high aspect ratio, but really starts to bite you if you have an aspect ratio of like 2-3 or something like that, right? Okay, so that's for an elliptical wing. Now let's actually consider the same scenario for a little bit different aspects. So instead of looking at the wing, which has a bunch of vortices coming out and induces a flow on itself, consider this horizontal tail, which is both subject to vortices coming out of itself and the vortices coming out of the main wing, right? It is subject to the vortice coming out of the main wing even at a more significant, it got an influence that's more significant than what we discussed on the last slide. Why? Because if you consider the downwash on the wing, first of all, it has no effect from the bound vortex because the bound vortex is aligned with the location we're analyzing. And it suffers from about half of this like infinite vortex, right? So remember, like the induced flow is proportional to the sine of this angle versus minus the sine of that angle, right? And sine of this end is 0, sine of this angle is 1. So it suffers from half of like an infinitely long vortex. However, if you look at this point, if you look at the horizontal tail, it suffers from the same vortex but with a larger angle, right? So instead of suffering from half, the sine of this angle is almost like if you think about this as 45 degrees, then the sine of this angle is like 0.7. So as opposed to half, it suffers from like maybe 80%, right, of a infinitely long vortex. Plus, it has this bound vortex. What is the induced flow of this bound vortex on this point? this vortex on this point. Downward, exactly, right? So basically, this the induced flow from the main wing can easily on this point on the tail can easily be 3 times as strong as the induced flow of the same wing on itself. So the induced flow on the tail can be several times larger than the green one. All right. And the plus, the horizontal tail does not affect the wing much because all the vortices goes downstream, and if you think about the downstream vortices to upstream flow, it's very minimal. But it does have an influence on itself, right? So basically, if you think about the in the previous slide, we looked at how the induced flow alpha I is a function of CL, right? So the alpha I on the horizontal tail can be a much stronger function of alpha infinity, the angle of attack. So what is the result of that? So if you think about the previous plot, right, the gap between these lines are due to the induced angle of attack. So what this means is that if you think about the CL on the horizontal tail versus alpha infinity, right, the deviation of that from the 2 pi alpha infinity line is going to be the gap is going to be much larger. All right, does it make sense? Right, so basically, if you change the overall angle of attack, the strength of vortices on the main wing is going to increase, and the induced flow due to the strength of the main wing, the strength of the vortices coming from the main wing on the horizontal tail is much stronger than the effect of the induced flow on the main wing itself. Right, as a result, the angle of attack seen by the horizontal tail, right, is not going to be as sensitive to the overall angle of attack than the angle of attack seen by the main wing, sensitive to the overall angle of attack. So what's the consequence of that to the effectiveness of the horizontal tail? Right? Why do we use horizontal tail over here? Yeah?
I guess you have more control, like more control and stability.
Yeah, you have more control is one thing, stability is another thing. Control is done by like actually an elevator moving, either changing the camber, right, having or moving the horizontal tail as a whole, right? But the horizontal tail over here existing is for stability, right? Okay, so the stability, I mean, right now, just think of stability as if you just add a fin over here, right? This thing, as you increase the angle of attack, is going to push the airplane up. As you decrease the angle of attack, is going to push the tail down, right? That kind of orients the airplane with respect to the free stream, right? That's basically the effect of its stability. But the thing about this analysis is that how much lift the horizontal tail gets is actually going to be a much smaller function, a much less sensitive function of the free stream angle of attack than you would naively think, right? Okay, so if there is no main wing, then the horizontal tail would work very effectively. But if there is a main wing, the horizontal tail would not work as effectively, especially if the main wing has low aspect ratio, right? Or if the main wing has comes with a strong vortices from the main wing. So that's actually especially important if you look at some of the newer concepts. That's actually one of the startups coming out of this department called Electro-Aero, and it uses electrical propulsion to have an array of propellers blown onto the main wing. with a very large set of flaps, right? As a result of that, you can imagine the flow. This is a CFD calculation. The flow can deflect like at extreme angles. The result of that is the vortices, as you can imagine, coming out of the tip of the flaps can be extremely strong. And as a result of that, if they placed the horizontal tails, right? I mean, notice the location of the horizontal tails. Like, where is it? Is it different from like a usual placement of the horizontal tails? Yeah, they put it on top of the vertical tail, right? As opposed to over here. Why is it? Yes, to put it as far away from the vortices which comes down, right, as possible. To actually avoid as much as possible the reduction of its effectiveness. Okay, this is a very interesting scenario. If you place the horizontal tails down as opposed to up, in takeoff and landing conditions, the horizontal tail actually does harm other than help for the stability of the airplane. All right, so at some location, the horizontal tail effectiveness, right, which is proportional to the slope of lift with respect to angle of attack, is actually going to be negative. So this line can, the gap can be so large that this line can be actually negative for extreme scenarios. Okay, questions? No? Okay. So let's actually analyze some additional scenarios. So we looked at the straight wings. For example, if you have a forward swept wing, the vortice is coming out like that, and the inner part of the wing is almost similar to a horizontal tail, right? It's located behind the start of the wingtip vortices, right? So the effect of the wingtip vortices on the inner portion of the forward swept wing is actually stronger than it is for the straight wing, right? So the forward swept wing, the inner portions are almost like have similar effect as horizontal tail in the sense that the sensitivity of their angle of attack with respect to the free stream angle of attack is going to be less sensitive, right? It's going to be a lot smaller than 1 than the tip of the wings. Now for the normal backward swept wing, it's actually the opposite. Okay, so for the backward swept wing, actually a very interesting scenario is the opposite of this. So if you have a bunch of vortices coming out of the wing, think about the extreme tip of the wing. It is subject to a downward, well, if you think of this portion, it is subject to a small part of the vortices from the very tip, but it is subject to the upwash of less stronger but more vortices from the inboard of the wing. And the effect from the inboard treating vortices are stronger because it actually, this one sees more of the angle, right? So as a result of that, for some sweep wing designs, the sensitivity of the tip angle of attack with respect to the free stream angle of attack can be greater than 1. Okay, so it is so if you look at the tip cross section, and if you look at the alpha infinity CL curve, this can be slightly greater than 2 pi alpha infinity, right? While for the forward swept case, the inner part of the wing has the least slope, right? So basically, this kind of analysis is going to be useful when you want to optimize the lift distribution for multiple angles of attack, right? Not only you have to consider you have to consider 3 things, right? One is the distribution of the coordinates. So going back to this loop, if you have if you want to optimize the lift distribution for multiple angles of attack, you have multiple things you can tune. You can tune. Okay, so I should add something over here. There is also plus CL0, right? So I think no, this is the elliptical slide. Sorry. On this slide, right? So you can tune CL0, which can be tuned by changing the airfoil cross sections and twist the wing, right? So if the different cross sections are at different incidence angles, then CL0, the zero angle of attack CL, is going to be different. Okay, you can change the plane form, how the chord depends on the Y locations. That changes how the CL translating to the lift per span. Okay, you can also right. So basically, these two things are the main things you change once you have a sweep. Basically, the sweep is going to change how the trailing vortices affect the induced flow on the wing. Right. So as we analyze if you have different sweep angles, the sensitivity of the induced angle with respect to the strength of the trailing vortices could be quite different. All right. So this is all good considerations you can do for wing designs, especially for designing the plane form of the wing. Okay. Let me just say a little bit more about the lift and the induced drag in ground effect. So that's another consequence of the additivity of potential flow. So if you have a wing operating near the ground, the effective flow field is the trailing vortex system plus an imaged vortex. That is basically the opposite. If you think of the ground as a mirror, right, and you look at the trailing vortices inside the mirror, these are the vortices that is beneath the ground. And the result is that the induced flow field on the ground is going to be exactly horizontal. There is no vertical component because the vertical component from all of these cancel out. And you can look at this whole system to analyze what is the lift and the induced drag of the airplane in ground effect. I'll just jump to the conclusion is that the sensitivity of lift coefficient with respect to the free stream angle of attack is going to be much closer to an infinite span case, right, than when the airplane is away from the ground effect. And also the kinetic energy and pressure downstream due to the vortex system is going to be significantly reduced, especially when this image vortex is closer to this vortex than the distance between the two wingtips. So if the height over B is small, then induced drag can almost be the majority of the induced drag can be eliminated by flying in ground effect. All right, so that's basically our analysis of looking at the flow around the airplanes at the length scale of a span. Right. Starting from next week, we'll further zoom in and look at the flow field around an airplane at the length scale of the chord, right, which really starts looking at airfoils. All right. Okay. See you next Monday. Yeah. Oh, and the homework this week we are going to be using AVL to do a bunch of analysis. All right. So that's going to be the one due next Thursday. Yes.